So after talking about the basics of triangles, we're now specifically going to talk about right triangles. So if you're trying to solve a right triangle, you're either solving for missing side lengths or angle measures. So there's two methods for both. So if you're solving for missing sides, the first method is to use the Pythagorean theorem. If two side lengths are known. So you can only use the Pythagorean theorem if you know two of the side lengths. Otherwise, we're going to use trigonometric ratios. If one side and one additional angle are known. So we already know, because it's a right triangle, we know that one of the angles is 90 degrees. So we do have to know one additional angle other than that to solve for a missing side. If we are solving for missing angles, obviously the easiest method is to subtract from 180 if two angles are known. That's obviously your 90-degree angle and some other angle in the triangle. The other method is to use inverse trig ratios if so it should just say two sides. So use inverse trig ratios if we know two sides and we're trying to solve for one of the angles other than the 90-degree angle in the triangle. Okay. So trig ratios. So in trig ratios, we label the three sides of our triangle as opposite, adjacent, and hypotenuse. Okay. Now the opposite and adjacent sides are labeled based on which acute angle is picked. So for example, if I'm looking at angle A, my opposite side is the one directly across from it. My adjacent side is the one next to it. Now the hypotenuse is easy because in a right triangle, the hypotenuse is always across from the 90-degree angle. If I were looking at angle C, the opposite side directly across from it, the adjacent side directly next to it, the hypotenuse is still the hypotenuse. So for our trig ratios, we've got sine, cosine, and tangent. Sine is the ratio opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. It's just a little refresher of SOHCAHTOA for you. Within right triangles, there are two types of special right triangles. The first one is a 45, 45, 90. Now that describes the three angle measures. So two of the angle measures, the ones other than the 90-degree angle, measure 45 degrees. The two legs are the same, which we always denote with our variable x. And then the hypotenuse is the length of a leg times the square root of 2. So I should say in a right triangle, generally speaking, the sides that are not the hypotenuse are called legs. So we draw a right triangle, and it's not going to be drawn to scale. So we've got 45 degrees, 45 degrees. Our two legs are both x, and then our hypotenuse is that leg times square root 2. The other type of special right triangle is a 30, 60, 90. So obviously one angle measures 30 degrees and the other measures 60 degrees. Now here we let the shorter leg be x, which is across our 30-degree angle because that's the smaller angle. The longer leg is x times square root 3. And then the hypotenuse is 2x. So again, if we have a right triangle, we have our 30-degree angle, we have our 60-degree angle. The side opposite the 30-degree angle is x. The longer one is x squared root 3, which is across from our 60-degree angle. And then our hypotenuse is 2x. Now, both of these relationships, the 30, 60, 90 and the 45, 45, 90, were kind of discovered accidentally based off trig ratio. So it's not like they went out to look for special relationships. It's something that was discovered while looking at right triangles. So let's go ahead and solve for some missing side lengths and or angle measures in some right triangles. So our first right triangle here, angle O is our right angle. We want to solve for the third side. All right, if I don't know, and I could solve for missing angles as well once I know side lengths. But for right now, we're going to solve for BG. So we're going to use the Pythagorean theorem. So we have 14 squared plus 5 squared equals x squared. 14 squared is 196. 5 squared is 25. 196 plus 25 is 221. Then we take the square root and we get that x is 14.87. And then because we do have labels for our side lengths, it is in millimeters. Our next example, I'm going to be solving for the measure of angle A. So I know I know two of my side lengths. I know the one angle is 54 degrees. So this is a case where I can do 180 minus 54 minus x. Sorry, 180 minus 54 minus 90. And that will give me my missing angle. So we get 36 degrees. I could also solve for the hypotenuse. Okay. Next example, I only have one side length and one angle, and I want to use that to solve for angle M. So in this case, I have to use an inverse trig ratio because I don't have, I want to solve for the missing side length, ER. So I'm going to use the fact that I know that I have the angle of 22 degrees and I know my hypotenuse is 24 and I want to use that to solve for ER and I want to solve for EM. So the first thing I'm going to do is solve for x. So based on our 22 degree angle, x is the adjacent side to that angle. My hypotenuse is the 24, and then y is the opposite side. So that tells me which trig ratio to use. So adjacent and hypotenuse is cosine. So I know cosine of 22 equals the adjacent side x over my hypotenuse of 24. So to solve for x, I'm going to multiply both sides by 24. And I'm going to do 24 times the cosine of 22. Now you do need to make sure that your calculator is in degree mode for this. And if you want to make sure, just ask me. And we get 22.25, and then it would be inches. To solve for y, again, so we know that the opposite is sine. So sine of 22 equals the opposite side y over 24. Multiply both sides by 24. And 24 times sine of 22 is 8.99 inches. I'm actually going to go back to the previous example, and I'm going to show you how you could solve for that 36-degree angle if you didn't know angle C was 54 degrees. So I would set up using a trig ratio based off angle A. So the 12 centimeters is the opposite side, the 18 centimeters is the adjacent. So that gives me tangent. So I know that the ratio for tangent for that angle is 12 over 18, and that equals angle A. Inverse trig ratios say just do the inverse of that to both sides, and that will give you the angle measure. So we do tangent inverse of 12 over 18, and that will give us our angle measure. To get to the inverse, you just hit second and whatever that trig ratio is. So second tangent, and then I type 12 over 18. And I get 33.69 degrees. So as you can see, my triangles are not drawn to scale. So that angle is not 54 degrees. So we should definitely go with what I did with the tangent. We should definitely go with the tangent one on this. And I'll make sure on future things to make sure that my triangles are accurate in their angle measures. So let's talk about our special right triangles. So I don't really have to draw them for you because we already know the angle measures. So we want to find the remaining side lengths in a 30, 60, 90 special right triangle whose shortest side has a length of 3 centimeters. So I can draw the triangle just to kind of have a reference of what it is going to look like. Again, triangle's not drawn to scale. So 30, 60. So my shortest side has a length of 3. And we know the relationships that exist between the other two sides. So that means my longer leg is going to be 3 square root 3. And my hypotenuse is going to be 2 times 3, which is 6. Next, we're going to look at a 45, 45, 90 special right triangle. We know the hypotenuse has a length of 7 square root 2. And we want to find the legs. I should put units on these because I know they're all centimeters. So the hypotenuse is 7 square root 2. And we know that the hypotenuse, the relationship is the side length x times the square root 2, which tells me my legs are just going to be 7. Next, we want to find the lengths of the legs in a 30, 60, 90 special right triangle whose hypotenuse has a length of 32 millimeters. So we know that 2 times x, it gives us the 32. So we divide by 2. And that tells me that my shorter side is 16, which then tells me my hypotenuse is 16 square root 3. The last one, we want to find the length of the hypotenuse in a 45, 45, 90 special right triangle if the legs have a length of 2 feet. So the hypotenuse is just the leg times square root 2. There we go. So not a lot of difficult math involved in solving for side lengths in special right triangles. Let me know if you have any questions about the special right triangles or solving for angle measures or side lengths in a regular right triangle.